Hi, everyone. In this video, we're going to go over chapter 22. So we're going to focus on the difference or the t-test for two means or comparing two means. And this is what we are going to go over. So don't worry about memorizing those formulas. So we're going to use Excel and how we can calculate the difference in means into samples. And let's go right into it. And so I'm going to close this guy and I will let you go over that. But when you go to Blackboard, I have the same file, which is examples for t-test here, and then examples for t-test means here under training. So under training, I'm going to put this video right now over here. So that way you can watch it and follow along to submit your training for what we are going to do right now. All right, so this is the file that I have. So the first thing that we need to know is when we have two samples, right? So we have sample one, and then we have sample two. So we need to first decide whether they are dependent or independent, right? So sample one, whether it is dependent or not dependent. So the samples are going to be dependent when we are comparing the same person action at one point to a different point, right? So for example, if I want to compare the performance of students in a test when they were freshmen, and for that same student, I got their score when they were freshmen, and then I tested them again when they were sophomore. Or in other words, you can say that you tested, for example, the performance of particular or employees before an intervention. So you tested the performance of each employee before an intervention. And then after you did that intervention, let's say that you motivated them and you give them incentives to exercise every day. And then after, let's say, 3 months of them going to exercise every day, you tested their performance and then you compare their performance before and after. So that's what we call a paired test, or that's when the samples are dependent, right? So if the samples are different, so we have students who are right now sophomore and students who are freshmen, they are totally different uh, uh, samples, then we call that independent sample, right? And then if we have an independent sample, then we are going to look at, so we are going to use the independent t-test. So then we need to see, to run an f-test, and I will show you how to do that, which will tell us whether we should use the t-test assuming equal variance or t-test assuming unequal variance. And then we are going to use the correct t-test to compare the means, right? And to test our hypotheses. So let's start with an example here, test with equal variance. So this is an example, and I already have the solution here for you, but we're going to do it again. So we have, in a packing plant, we have a machine packs cartons with jars. It is supposed that a new machine will pack faster on the average than the older machine. To test that hypothesis, the times it takes each machine to pack 10 cartons are reported in the table here. So now the data provide sufficient evidence to conclude that on the average, the new machine packs faster? So for that, we need to perform the required hypothesis test at the 5% level of significance. So the first thing that we need to do is to answer this question. First step, are these independent samples? Is the new machine the same as the old machine? No, they are not. So, in other words, we can say those are independent samples because we have the new machines and the old machines. They are different or separate. Then the second step is, do they have equal variance? So for this, we need to use the F-test that we looked at the roadmap. So we use the F-test. So to do the F-test, so we are going to go to data, and then from data, we go to data analysis, and then we should find the F-test to sample of variance. And then for variable one, it is going to be this guy. I will select the label as well, and I will make sure that I check the label as well here. So that's for the first one. And then for the second one, I'll select this guy. And then that's my the alpha, which is 0.05, which is the 5%. So you can put your output anywhere you want. So for me, I like to put it somewhere here. So I'll put the F-test first here. So now, based on this, we can see that the p-value, so the p-value here is actually greater than 0.05, which tells me that they are so greater than 0.05. That means they are equal variance. So let's go back to the roadmap. So if the p-value is greater than 0.05, then it is equal variance, right? So now that's equal variance. Now I need to do the correct test based on the roadmap. Then I will do independent test with equal variance, with assuming equal variance. So to do that, we are going to go to data and then data analysis. And then I will look for the t-test to sample assuming equal variances. Because if it was not, then we will select the unequal variance. So now we will select assuming equal variances and say, okay, now we're going to select this guy. And then I'll select this guy. So the old machine, the new machine, and the old machines. And then the output, I'm going to put it right here. So now I have done the t-test, right? But now which one should we look at? The p-value for two tail or one tail? So here, since we already have decided that we wanted to know if the new machine is faster, that means greater, right? If it was equal or not equal, then we are going to use the two-tailed as we discussed in the previous lecture. But now it is faster, that means greater, right? And then we are going to, in this case, we are going to use only one tail, right? Because we have decided what is the direction. And the p-value is way less than 0.05. So less than 0.05. That means there is a significant difference between the new machine and the old machine. So in other words, here the new machine takes less time, which is faster than the old machine, as you can see in terms of the means. So now we can conclude that. So the p-value is here actually. And the p-value here, it is supposed to be this one. 0.01. Right? So now we can say our conclusion, we apply the corresponding analysis to find the conclusion. So again, our conclusion need to be considered is the null hypothesis, alternative hypothesis. So is it one tail or two tails? In this case, it is one tail, right? Because we said it is going to be faster. Your machine packs faster. So that's one tail. And then now our conclusion is the data provides sufficient evidence to conclude that on average, the new machine packs faster, right? So this is for the first example. Right, so now let's look at another example where it has unequal variance. So the first step is to ask if the samples are dependent or not dependent. So we are collecting data from at the same time from sophomores and juniors. So they are not the same person. This one is not the same person like this one. So that means they are independent samples, right? So the first step that we want, so we already know that those are independent samples. And then the next step is, do they have equal variance? So we'll go the same thing. We'll just go to data, and then we'll go to the F test. And then we'll select this guy. So we notice also we don't have the same sample. So we'll select whatever we have, doesn't have to be equal. And then we have label selected. And then this guy, I'm gonna put it here. All right, so now you can see that the F test shows that, or the p-value shows that there is significant difference. So that means they are not equal. So again, so the variances are not equal. So unequal. So that means we are going to move on to the next step, which is we are going to use t-test with unequal variance. So data. So then we're going to go to t-test assuming unequal variance. So range 1, it's going to be this guy. Range 2, this guy. Then label. The output, I'm going to put it here. So now let's look at the p-value. Again, the p-value, which one? Is it the one-tail or two-tailed? Here, let's look at the statement here. There are 2 random samples of 17 sophomores and 13 juniors attending a large university. Yield the following data on grade point average at the 5% significance level. Do the data provide sufficient evidence to conclude that the mean GPAs of sophomores and juniors at the university differ? So that means, are they equal or different? So equal or different. So we are not claiming someone is greater than the other. So now, since we have the equal, that means they are two-tailed, right? So in this case, we are going to use the two-tail. And then we'll look at the p-value here. So the p-value is larger than 0.05. So this allows us to conclude that there is no significant difference between the GPA of sophomores and juniors. So in other words, our conclusion says at the 5% significance level, the mean GPAs of sophomores and juniors at the university might be the same, or they are not different, right? May, right? We don't say they are different. We say may or might be the same, right? So they are not different. So now let's move on to the next one, which is the paired t-test. So again, we are collecting data from the same person, from the same student, when they were sophomore and when they were junior. So now those 2 samples, they are not independent, they are dependent because we are using the same person data, right, when they were sophomore and junior. So again, going back to the roadmap, 2 samples, are they independent or dependent? So they are dependent. That means we are going to use the paired t-test. Right, so go back here. So again, here the question is, the random sample is collected from 13 students who attended a large university on grade point average of sophomore and junior. So do the data provide sufficient evidence to conclude that the mean GPAs of the sophomores and juniors at the university differ for the same student? Here, that's the key. The same student is the key, makes us to conclude that they are dependent samples. So again, here for the first question, are these independent samples? No, they are dependent samples because we're collecting data from the same person. Second step, apply the corresponding analysis to find conclusion. So again, based on the roadmap, we are going to use the pair t-test as it is provided to us under data and data analysis tool pack. So, so we have here t-test paired to sample of for means. So pair, so we're going to use pair 1 or variable 1, and then variable 2, make sure that the labels are there. And then I like to put my output here. So again here, is it one tail or two tail, right? Since it says differ, meaning are they equal or not equal, right? So that's the question. They didn't say greater or less than. So that means if they say differ means not equal or equal, that means two-tailed. We look for the two-tailed p-value. And again, the p-value here is greater than 0.05. So this allows us to conclude that there is no significant difference between sophomore and juniors GPAs. So again, this is two-tailed, and we're going to use that p-value. So at the 5% significance level, we conclude that the mean of GPAs of sophomores and juniors at the university might be the same, so they are not significantly different, right? So that's the way we answer it. Either way, you answer it this way, or the way I said it, they are not significantly different, will work as well. All right, so now I like to go over the project data that you have already cleaned. So what I'm going to do is to randomly select a categorical variable, which is gender. So let's say male versus female, and then isolation, right? I'll select those two, and then I will put them here. And this is just an example here for you. So we go back. All right, so this is what I have for you. And now, so this example is a hypothetical example. So it says past literature reports that females feel more isolated than males. Based on the sample data you collected for your class project, test the hypothesis to answer whether females feel more isolated than males. So do the data provide sufficient evidence to conclude that on average, the females are more isolated? Perform the required hypothesis, test at the 5% level of significance. So, right? So now we have isolation, which is considered continuous variable, and we have gender, which is categorical variable, but we measure gender as females, male, and indifferent, or unidentified. So for us, let's clean this data first. So I hope it doesn't move these things here. We'll just perfect, you can move those. All right, so now we have female and we have males. And then in the bottom, we have prefer not to say. So in this case, since they are not relevant, we are interested in males and females, so we can remove those. You can use the data as is here, but you will need to scroll, or you can clean it, where you can put isolation for female in one column, isolation for male in one column. That will work as well, right? But if you want to keep it this way, that will be fine. So let's do that. So for this, we are going to decide whether those two samples are independent or not. So we have males and females. They are different, right? So they are separate samples. Sample for females, sample for males. So definitely they are independent. Now the second step, so they are independent. The second step is to do the F test to see if they are unequal variance or equal variance, right? So to do that, we are going to do the F test. So we'll go to the F test. All right, so the first variable one, which is females, I'll just select the isolation only for females, and I'll scroll down until I reach the last female here, right? So that's for females. And then for males, I'll just go from where we stopped here. So for males, because the male's next to them, right? So that's the isolation score for male until I reach the last one. So labels, I don't have labels here, so I'll uncheck that. And then where I want to put my output, I want to put my output here. All right, so now let's look. So the p-value, it is not significant, which tells us that the variances are equal, right? So they are equal. So again, they are equal variances, and the p-value is this guy. I can just copy this guy from here and put it here in the question mark. And then, so the next, since we already know based on the roadmap, it is equal variance. So we will do the t-test, independent t-test with equal variance. Right? So again, I will go to data analysis, and then I will do assuming equal variances. Right? And I'm going to select this guy from here all the way for female. And then for males. Right, so now I will put this guy. So I don't have labels, so I'll need to make sure that I uncheck when I don't have labels. So I will put this guy here. My results. All right, so now let's decide whether it is one tail or not, whether it is one tail or two tail. So in this case, based on the hypothesis statement here, females are more isolated. Are females more isolated? So that's basically what we tested. More, that means greater or more, right? So it's not equal or not equal. Equal or not equal means two-tailed. Something greater or faster or lower or less, right? In that case, we have that one tail. In this case, we're going to look at the p-value when it is under the under one tail. So this is the p-value. So now, since the p-value is very low, lower than, so remember that motto that we talked about. If the p is low, the null must go, right? So since the p-value is very low, that means there is a significant difference between females and males when it comes to isolation. So let's look at the mean for female is 2.3 in comparison to only 2. So females feel more isolated than, at least in our sample, than the male's sample. So in other words, so we can conclude now, the data provides sufficient evidence to conclude that on the average, females feel more isolated than males. So I hope this helps kind of to introduce for you the t-test for means, and I will see you soon. So thank you all.